Let's calculate some probabilities based on the binomial distribution. So imagine that we're flipping a fair coin, and just like in your lecture notes, if you're doing a small number of trials, you can actually construct a table for outcomes. So if we have a coin, 50% of the time comes up heads, 50% of the time comes up tails, we should be able to figure out what our expectations would be for various combinations of heads and tails. So we make our table as we did in the lecture notes. The first 4 columns are just the first 4 trials, right? So trial 1, 2, 3, and 4. The 5th column, n sub h, that's the number of heads, n sub t is the number of tails. The sum of n sub h and n sub t has to sum to 4, right? Because you did 4 trials and the coin never lands on its side or falls off the table or anything like that. The final column, n sub c, tells you the number of combinations that lead to a particular outcome. For example, let's pick that top row of data. If we want to get out 4 heads, there's only one way to do that, so the number of combinations is 1, right? You literally have to flip a head every single time. However, if you wanted instead to have 3 heads and 1 tail, well, you can see that there's 4 different ways to do that. You could have the 3 heads at the beginning and then tail at the end, tail at the beginning, 3 heads at the end, or you could have the tail in trial 2 or trial 3. That's 4 ways of getting the same outcome fundamentally, which is 3 heads, 1 tail. If you have 4 trials or less of a fair coin flip, then sure, make the table, you can figure out all of the statistics. What we can imagine, though, is that we're going to run into problems where the number of trials is much larger than we would ever want to draw out in a table. So what I want to do in this exercise is go through, figure out how to use the binomial distribution first to predict the values in the table, and then for a problem that we could never construct a table for. Alright, so let's start by writing down the binomial distribution. So we do that over here. And I want to walk through what some of these variables mean. So on the left-hand side, P is just the probability of some outcome. But it depends upon 2 variables, k and n. Let's start with k. So k is the number of successes. What that means is that if you're flipping a coin and you just want to know how many times you get heads, if you consider it a success to get heads, then k would be the number of times you get heads. So what you can imagine is that you go through and you want to know what your odds are of flipping 3 heads out of some number of trials, you would set k to 3. N is just the number of trials. This is relatively easy to track for a coin flip problem. That's just the number of times that you flipped the coin. Okay. There's one other detail we have to deal with here. Maybe you haven't seen it in a while, and that is a factorial. So that doesn't mean that you just say n really loudly. It doesn't mean we're excited about n. What n with an exclamation point after it means is that you take n times n minus 1 times n minus 2 dot 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 all the way until you get down to 1. You should stop at 1. Don't go to 0 or else everything factorial is 0. That would be weird. Okay, that's how factorials work in case you don't remember. So now we're going to go through and actually try to compute the chances of getting a total of 2 heads and 2 tails. Just to be clear about the setup for this problem, we don't care the order. We just want to know that we do 4 trials and our total outcome will be 2 heads and 2 tails in any order. Well, what do we choose for our k and n values? Let's say that we consider it a success to flip heads. Then in that case we choose k equal to 2. The total number of trials has to be the total number of coin flips, which is obviously 4. Okay. So now we want to go through and apply that with the binomial distribution. So the probability as it depends upon k equals 2 and n equals 4 is now 4 factorial divided by 2 factorial. Also in the numerator is 4 minus 2 factorial, which of course will just come out to be 2 factorial. And then the whole thing is times 1 over 2 to the 4th power. So we can simplify some of this. You can see what happens to 4 factorial in the numerator. 4 times 3 times 2, technically also times 1, but that doesn't do a whole lot. We've got 2 powers of 2 in the denominator, and then 1 over 2 to the 4th becomes 1 over 16. That tells us that the probability of 2 successes out of 4 trials for a fair coin is 3/8 or 37.5%. Now how does this compare to the result from our table? Well, we can look and see 2 heads and 2 tails. That corresponds to the big middle region there that has a total of 6 combinations, right? Because you could do it in a bunch of different orders. So that's 6. How does that relate to 3/8? Well, the total number of combinations over here on the left, we circle all those numbers. So it's 1 plus 4 plus 6 plus 4 plus 1, that's 16. So 6/16 should have been the probability of getting 2 heads, 2 tails. Well, that's nice. 6/16 reduces to 3/8, right? So we get exactly the same value from counting states as we do from computing the probability using the binomial distribution. That was an easy one, though. What I want to do now is to do a computation where you just wouldn't want to make this table. It would be too big. It would run off into the next video. We can't have that. So what if we considered a case of 500 heads and 500 tails? We have to choose new k and n values, because we did a total of 1,000 coin flips in that case, so k in this case would have to be 500, n would have to be 1,000, and there's no way we're going to make a table out of that. Let's just get rid of the table right now. Alright, so what are the chances of getting exactly 500 heads and 500 tails? Again, the order doesn't matter, total of 1,000 coin flips. Well now, k becomes 500, n becomes 1,000. Uh-oh, this is going to be a little tougher to evaluate. Unless you want to sit there and write out 1,000 times 999 times 998 and so on, it'll take you a while. Maybe you try entering it into your calculator. Well, guess what? Calculators can't always get these big factorials either. That's going to be a big number. So fortunately, there's an approximation we can use. And it's called Stirling's approximation, and the thing I like about it is that it totally seems like it's not going to help, but it does. So Stirling's approximation is that n factorial, and this doesn't have to be the number of trials, n can be anything there, anything factorial, as long as it's a large number, can be approximated by n over e, where e is the base for the exponential function, that in parentheses raised to the n power times the square root of 2 pi times n, all under the square root. So that's true anytime you have large n. Certainly 500 and 1,000 are much bigger than 1, that counts as large. Okay, so how is that going to help? Because it seems like that's at least as complicated as a factorial, right? Well, let's see. So we'll use Stirling's approximation. And I'm just going to outline where each of these terms comes from. So the thing in the denominator right here, that's just 1,000 factorial, right? So I applied Stirling's approximation just to 1,000 factorial. And then I did it again twice in the denominator. So I did it once for 500 factorial, which is that first set of terms. And then over here, we have another 500 factorial, right? Because 1,000 minus 500 factorial is 500 factorial. So that's where all the stuff comes from in the new expression. 1 over 2 to the 1,000 is unmodified over there on the right. Okay, so how does this help? Well, maybe you can see how it helps. One way is that those 500 over e to the 500 power, two of those in the denominator, you can combine those because both of those things raised to the 500 power have the same base. The base is 500 over e. So what does that mean when you multiply them? That means that you just add the exponents. So that's really nice. That will become 500 over e to the 1,000th power. Alright, so if we do that, then in the next line you can see that we have 1,000 over e to the 1,000th power times square root of 2 pi 1,000. Then in the denominator, 500 over e to the 1,000th power. Now that's times 2 pi over 500 without the square root because we had two of those in square roots in the previous expression. Okay, I think I said all that right. Well, how is this helpful? Maybe you can see it. Now we have two things raised to the 1,000. That's kind of nice because that means that you can bring in their bases into the fraction, and if you do that on the next line, that just becomes 1,000e over 500e all to the 1,000. Well, that would normally be very messy, but the e's cancel, and actually you can see that 1,000 over 500, that's just going to be 2 to the 1,000. That's nice, and the reason that's nice is because we actually have another factor of 2 to the 1,000, this time in the denominator. So those two are actually going to cancel. It worked out nicely that I picked P500 and not P501. That would have made our lives a little bit worse. But in this case, we can do the calculation in a relatively straightforward fashion. The answer is just going to be the square root of 1,000 divided by the square root of 2 pi times 500. Okay, so we can do that. That you can handle in any calculator. And you get that the probability of exactly 500 heads out of 1,000 trials is 0.025 or 2.5%. So it's not incredibly likely. That's the interesting part of this outcome. It is the most likely single outcome, meaning that it would be less likely to get like one head out of 1,000 trials or one tail out of 1,000 trials by a considerable margin. But actually getting 500 heads, it's not a guarantee by any stretch of the imagination. The chances are only 2.5%. The most likely outcome is that you'll have something other than that. Now it'll probably be close to 50-50 odds, meaning close to 500 heads, close to 500 tails, but the chances of you actually getting exactly 500 heads are pretty slim, 2.5%.